Today we are going to talk about half-life of a reaction and pseudo first order reactions. Now, what is half-life of a reaction? The half-life of a reaction is the time in which the concentration of a reactant is reduced to 1/2 of its initial value. In other words, we can say that half-life is the time required for completion of half of the reactions. It is represented as T half. For zero order reactions, we have already derived in our previous class the expression for rate constant, the integrated rate equation for rate constant of zero order, and which is written as K, which is the rate constant, equal to R naught minus R upon T, where R naught is the initial concentration of the reactant at time t equal to 0. R is the concentration of the reactant after time t has passed, and T of course is the time, which is generally taken in the unit of seconds. So from this integrated rate equation we can derive the expression for half-life of a zero order reaction. So how do we proceed for that? So in place of T, we'll consider time to be as the T half value. So when time is equal to T half, then at that time the concentration of the reactant is reduced to half of the initial value. Since the initial value is R naught, so R will be equal to half of R naught, that is R naught by 2. So now we can rewrite this integrated rate equation in terms of T half, and this is how we proceed. K is equal to R naught minus R naught by 2 divided by T half. We have replaced the term T by T half, and R we have replaced by R naught by 2. So again we rewrite it in terms of T half. So T half becomes equal to R naught divided by 2K. This is the final expression or derivation for the half-life of a zero order reaction. It is clear from this finally derived expression for T half that for a zero order reaction, T half is directly proportional to the initial concentration of the reactant, and it is inversely proportional to the rate constant, which means that if you are increasing the concentration of the reactant, initial concentration of the reactant, the value of T half will also increase. Now coming on to the half-life for a first order reaction. For a first order reaction, again we have already derived the rate expression, the integrated rate equation for a first order reaction, and it is written as K equal to 2.303 upon T log R naught divided by R. Here K is the rate constant, T is time, R naught is the initial concentration of the reactant, and R is the concentration of the reactant at time T. So once again, in order to derive the half-life expression, in place of T we will write T half, and when T is T half, then R becomes equal to R naught by 2, that is half of the initial concentration of the reactant. So when we put these values in this integrated rate equation, the rate equation now looks like K is equal to 2.303 upon T half log R naught divided by R naught by 2. When you solve this, you will get the expression in terms of T half as T half is equal to 2.303 upon K log 2. Log 2 value, if you look from the log table, it will come out to be 0.3010. So if we put that value of log 2 in the T half expression, the expression changes into T half equal to 2.303 into 0.3010 divided by K. And when you multiply these two numbers, you get the final value as 0.693. So T half now becomes equal to 0.693 divided by K, where K is the rate constant. So again, if you look carefully at this expression, you will find that the first order rate equation, when we are calculating its T half value, when we are deriving its expression, then T half, that is the half-life, is a constant value. There is no concentration term in the expression derived for it. That is, it is independent of the initial concentration of the reacting species. It is only dependent upon the rate constant, and it is inversely proportional to the rate constant of the first order equation. So from these two equations, that is for first order and zero order, you can calculate the value of T half. So finally we can conclude that for zero order reaction, T half is directly proportional to initial concentration, whereas for first order, T half is independent of the initial concentration of the reactant. Next we move on to pseudo first order reactions. The term pseudo means false, and first order reaction, we already know that reactions in which the rate is directly proportional to the concentration of the reactant raised to the power 1 are known as first order reactions. So what are pseudo first order reactions? So order of reaction is sometimes altered by conditions under which the reaction is taking place. For example, we can consider a chemical reaction between two substances when one of the reactants is present in large excess. In such type of reactions, what happens is that the decrease in concentration of that reactant which is present in large excess is so small that it is almost negligible, which means that as the reaction proceeds, one of the concentrations which reactants which is present in large amount, in large excess, its concentration, though it is changing, but it is changing to such a small extent that it is almost considered as if no change is occurring in its concentration. That is, the change is almost negligible. And two such reactions are quoted here as examples. The first one is hydrolysis of an ester, ethyl acetate. This reaction takes place when ethyl acetate reacts with water, giving you the acid, corresponding acid, and the alcohol. Here in this case the acid is acetic acid and the alcohol obtained is ethyl alcohol. Now, out of the two reactants, that is ethyl acetate and water which is a solvent here, it is present in large excess, and during the progress of the reaction, very small change occurs in the concentration of water. So that means that though it appears, this reaction appears as if it will depend upon the concentration of both the reactants, but it will be independent of the change in concentration of water. Another example, inversion of cane sugar. Cane sugar means sucrose, formula C12H22O11. Again, this reaction involves reaction of sucrose with water, and during this reaction, sucrose decomposes into its two monosaccharide units. One is glucose, another one is fructose, both of them having the same chemical formula C6H12O6. Now, in both these reactions, water is present in large excess, that is in the hydrolysis of ester case as well as in inversion of cane sugar, and in both of them the reaction is depending only on the concentration of the other reactant. In the first case, it is dependent on the concentration of ethyl acetate, and in the second case, it is dependent on the concentration of the sugar. So finally, we can say that such reactions which appear to be of higher order, means when you look at the reaction, it will appear as if the order is dependent upon the concentration of more than one reactant. So they will appear to be of higher order, but they will follow first order kinetics. That means they will be dependent, the rate of the reaction will be dependent only upon the concentration of any one of the reactant. Then such reactions are termed as pseudo first order reactions. Means they appear to be of higher order, but they are following first order kinetics in reality.